Okay, so on page 21, we're going to start looking at number 1. All right. Okay, so number 1. Good morning. So morning review, page 21. Number 1, it says we have 2x over x squared plus 1 on the closed interval. Determine max and min values. This is extreme value theorem. So extreme value theorem says I can find the max and min values if I test endpoints and critical points. So we know we're going to test -2 and 2, but we also want to see if there's any more critical points that can land inside this interval for us to test. One thing that we have to, there's one condition for extreme value theorem, and that is the function continuous? Well, if it's a polynomial, we know it's continuous, but if there's a denominator variable, we have to look for vertical asymptotes. And if I set x squared plus 1 equal to 0, am I going to find the vertical asymptote? Yes, thanks. What if I try to solve for x? Okay, so there's nothing that can cause the denominator to be 0, so there's no vertical asymptotes. If there's no vertical asymptotes, there's no disruptions. Our function is continuous. Okay, so let's find critical points. Critical points comes from f prime. So if we want to find f prime, we have to go through quotient rule here because of the numerator denominator setup. F prime g minus f g prime all over g squared. Okay, so now that we have f prime, we're looking for critical points. Critical points can either come from the numerator or the denominator. So it can either be a place where the slope is 0 or the slope is undefined. But we already discovered there's no real number from the denominator, right? We'll get imaginary if we look in the denominator. There's nothing from the denominator, only from the numerator. So we set the numerator equal to 0. So we get x squared equals 1. We take the square root. We get x equals plus or minus 1. Both of these critical numbers land inside the interval. So guess how many points we're going to be testing for max and mins? 4. Yep, 2 critical points and 2 endpoints. And they all go back into the original function. And we just compare their y values. Highest y value is your absolute max. Lowest is your absolute min. So they each get inserted into the original function. Don't plug into the derivative, into the original function. Now we're looking for location, right? We're looking for what is physically the highest and the lowest point on this graph. So at -2, my calculator gave me -0.8. At -1, I got -1. 1, I get 1, and at 2, I get 0.8. Okay, so the highest y value we see is 1. Lowest is -1. So just focus on the y values. I don't care about the x value. So you just say absolute max value is 1. Absolute min value is -1. Determinative Rolle's theorem can be satisfied by this function. Okay, so with Rolle's theorem, we just want to know can we guarantee a slope 0? So if I want to guarantee a slope 0, there's 3 conditions, right? Continuous, differentiable, and do the endpoints produce the same y value? Because if the endpoints produce the same y value, then I know that somewhere between the graph must experience a slope 0. Right. If I know that the graph is connected, no sharp turns, and the endpoints gave me the same y value, there must be a slope 0, guaranteed slope 0, somewhere between. So that's what we're looking for. Can I find the location of guaranteed slope 0 somewhere along that graph? Okay, so first we're looking at with a polynomial. So there's no variable in the denominator. This is gonna be a nice smooth curve. So our conditions will be met. So, well, at least the first 2. So you want to make sure you can write out your conditions. Continuous is with brackets, differentiable is with parentheses. Next condition is, do we have the same y value at the endpoints? Because if I do, there must be a slope 0. So I need to find what's happening at -2. I need to find out what's happening at 3. -2, I plug into the function here. -2 plus 2 is 0. Anything times 0 is going to be 0. I plug in 3, also 0. So I know the slope is going to be 0 because change in y over the change in x is 0 over 5, which is 0. Now, what if the two endpoints gave me 3 and 3? Do I say that my slope is 3? It's still what? Still 0, right? So remember, we're not setting the derivative equal to 0 because these are zeros, because we're saying that the derivative equal to 0 because the slope is 0, right? If my two y values are the same, that's enough for my slope to be 0. So now I know that my average rate of change is 0. So I simply set the derivative equal to 0. Now we could go through product and chain rule here, but maybe it's just easier to just FOIL this out. It takes a little bit longer, but I can just FOIL this out, distribute the x minus 3 through, and then it just makes it an easier polynomial without having to go through messier rules. So let me just clean this up. Eventually, I do want to set the derivative equal to 0. Right? I don't want to set this equal to 0, right? There's no calculus. I'm looking for x-intercepts. I'm not looking for that. I'm looking for slope 0, somewhere between -2 and 3. So if I just FOIL this out here, x squared plus 4x plus 4. Takes a little bit longer, but I can avoid product rule if I just clean this up a little bit more. Okay, so now that I have my f prime, or sorry, f of x, I can find f prime. And set that equal to 0. So now I have my instantaneous rate of change formula. Make it equal the average rate of change. Now I can just factor and solve, right? X squared plus 2x minus 8. Okay, both sides to be, let's see, I want the positive 2 here, so this gives me -8 3x squared minus 4x plus 6x plus 2. Okay, so I can solve for x now. X is 4/3 and -2. Right, set both equal to 0, solve for x. Remember, we are guaranteed that there's at least one place where the slope is 0. So we did find 2 locations, but we only care about locations that lands between. So -2 is out. It's not inside the interval. Well, it's also a duplicate too. Not duplicate, sorry. It has to be inside the interval. So this is not inside the interval, just 4/3. So at 4/3, the graph is going to be experiencing a slope 0. Okay, everybody, any questions with the steps for Rolle's theorem? So basically,
It says x equals -1/3 and x equals.
yeah, we're on number 2. But yes, 3 is 1 and negative 1/3. Okay, so Rolle's theorem, the basic idea is you're setting your instantaneous rate of change equal to the average rate of change, but then your average rate of change or the slope between the endpoints is always going to be 0, or it needs to be always be 0. Otherwise, we got to categorize it under MVT. We can't call it Rolle's theorem unless your average rate of change is equal to 0. Okay, number 3. Now determine if mean value theorem can be applied. Mean value theorem is not as restrictive as Rolle's theorem. We still need to check for continuity and differentiability. We're still going to find endpoints. We're still going to find slope. But Rolle's theorem, the slope between the endpoints has to be 0. Mean value theorem, it can be any number. As long as it's a real number, that's good enough. But still the same formula. We still set the instantaneous rate of change, which is our derivative, equal to our average rate of change. Okay, so again, we're dealing with a nice polynomial. There's no denominator to worry about, so our function will pass all the conditions, continuous and differentiable. And we can move on to our working to find our slope between the endpoints. Okay, f of -1 is 0. Let me test my other endpoint. Okay, my endpoints are different y values, but it's okay. I can still find the average rate of change, find the slope between the endpoints, subtract the y's, divided by the difference of the x's, change in y over change in x. So my average rate of change. So I know that somewhere along my graph, I can guarantee a slope -1. I'm looking for a slope -1 somewhere on this function between this interval. Okay, so next step, I can get it ready for power rule. I mean, I can go through product rule, but there's no need to go through product rule, especially if I can just do power rule just one step by cleaning up the parentheses. So we set the derivative equal to our average rate of change, right? Instantaneous rate. So we got to find f prime first. So here's my average rate of change. Here's my instantaneous rate of change. Set these equal to each other. Just like Rolle's theorem. It's just that with Rolle's theorem, you're always setting the derivative equal to 0. Mean value theorem, you're setting your derivative equal to, and may or may not be 0. Most likely it's not going to be 0, but it could be. Now, when I get to this stage here, can I do this? Can I say 3x squared minus 2x equals, put the coefficients together? I mean, put the constants together and then factor and solve. Can I do this? No, right. This has got to be a what? Got to be a 0, right? So I cannot, I know it feels easier to just do it this way, but you're not going to get the right answer. Okay, we cannot have this process unless it's not going to work unless there's a 0 showing up. So we got to move everything over to the left side first and then factor. Okay. Can't do that. Okay. -2, sorry. -2 plus 1 is -1. Now go through your trinomial factoring. Okay, solve for x. So we have two different locations on this curve where there's a slope of -1, but I'm only looking for what's between the intervals. So 1 is out, only -1/3 lands inside my interval. Okay, let's look at number 5, next page. Okay, so we went through 3 big topics within this unit: extreme value theorem, Rolle's theorem, mean value theorem. Page 22, number 5. Okay, so it says the derivative is shown. This is the derivative function. Which of the following is not true? Well, before we even look at our options here, why don't we create our slope and concavity sign line? Just good practice for us, right? We can. It's also good when we're trying to sketch out our derivative graph, be able to create our sign line. So let's go ahead and label what we know to be true. So we know that at A, there's a critical point because we're looking for slope 0. So on our slope sign line, we know that to the left of A, we see the graph is clearly below the x-axis. Don't look at the rise, look at the location. It's clearly below. That's enough for us to know my actual graph is falling. And then to the right, I know the graph is kind of showing this behavior, but it's all clearly above the x-axis. So my graph will only have a relative minimum. Okay. For my second derivative sign line, my concavity, I know that peaks and valleys are of the f prime is going to be points of inflection. So the only peak or valley that I see is at B. So we know that there is a point of inflection at point B. And then to the left, my f prime is rising. Whenever my f prime is rising, that means my slope is becoming more positive, which means that my actual graph is going to show a shape of concava. Whenever my f prime graph is decreasing, I know my slope is becoming more negative, so concave down. Okay, so everything that we need is in front of us here. Let's see which of the following is true, which is false. F of x has a relative minimum at x equals a. Is that true? Yes. We see that the arrows are telling us that we can expect a relative min there. This is true. Absolute maximum at x equals b. That is not true. That's a point of inflection. Point of inflection is not going to be a maximum. It's just going to be a place where the steepness is going to change. This is definitely not true here. So we think it's B, but let's just go ahead and confirm that all the others are true. F of x is increasing from A to B. That is true. Anything after A, my graph is increasing. F prime is positive. Slope is positive from A to B. That is true. From A to B, all my F prime graph is sitting above the x-axis. Above the x-axis means positive slope. F double prime of x is equal to 0. So we know that that is true. That this doesn't mean that this is guaranteed to be a point of inflection, but it is a candidate. But we know it's point of inflection because not only is a slope at B0, but there's a change in signs, right? You got from concave up to concave down. So this is also true. Okay, number 7. Which of the find extrema of the function? So we got a nice polynomial here. We can just go through first derivative test, right? Find that prime, create your sign line, and then look at your rise and fall of your arrows, and then we should be able to determine which of these is true. Solve for x, we get 5 and 7. Put them onto our sign line and see how the graph is moving on either side of these potential max and mins. Here I can test any number to the left of 5. I'll choose 0. I'll choose 6. I'll choose 8. They all get inserted into the f prime function. 0 minus 5 is negative. 0 minus 7 is negative. 2 negatives makes positive. And then my graph is rising. Okay, plug in 6. 6 minus 5 is positive. 6 minus 7 is negative. Positive and negative gives me negative. Positive times positive is positive. So look at the arrows here. We know the graph is rising, falling, rising. We expect a relative max at 5, a relative min at 7. P. Okay. Number 8 is just critical points. That's just basically just getting to this stage here. Set f prime equal to 0, solve for x. So that's not anything difficult there. Number 9, find the point of inflection. So point of inflection comes from which function here? We got to work our way down to what? Double prime. Now, let's say that this is a little messy with the derivative. Let me just give you the f double prime and see if you can go from there. So if let's say I already gave you f double prime. If I want to find point inflection, I set f double prime equal to what? To 0. Okay, so set The 8, there's nothing from 8 because there's no variable there. So 8 equal to 0 doesn't make any sense. We can leave that out. Can I, at this stage, stop and say that these are points of inflection? Okay. What's wrong with that statement? It could be true, but what else do we need to do? We gotta look at a sign line. All right. So if you stop here, it's possible that these are critical points. I mean, these are definitely critical points, but these may not be point of inflection unless you look at your sign change. So you got to go further than this. Now, if there's no sign change, then there is no point of inflection. Right? It's got to go from either positive to negative or from negative to positive. Okay. So we'll test points in each subinterval into the second derivative function. -5 in for x, that's negative. -5 in for x, also negative. 2 negatives makes positive. Now this is second derivative, so we don't do arrows here, right? We do cavity here. Okay. -3, positive times negative is negative. Plug in 0, positive times positive is positive. So is there a sign change at -4? Yes, that's a point of inflection. Is there a sign change at -2? Yes, sign change, negative to positive. Okay. So yes, we did confirm that these are both points of inflections. How can I find their y values now? Looks like they all have y values. Back to the original. Yeah. Plug in -4, I get 0. Plug in -2, I get -32. Okay, let's do a box problem optimization. But if you guys can use the space on page 25, this one we'll do a box problem here. Just use the space. I have a problem that I'm going to have you guys copy down. Okay.
We're not have to do that.
No. Yeah, there's one optimization problem. It'll be a box problem. Rectangle. We've been working on that over the past couple of days, right? Okay, so page 25, you guys can copy this problem down. Rectangular box with an open top has volume of 30 cubic meters. The box has a square base. Material for the base is $15 per square meters. Material for the sides material for the sides are $7 per square meters. Find the cost, surface area, dimensions of the cheapest container. Right, so how did you guys make the dimensions of your box? It's got a square base, so. What variables you guys use?
Where
Yeah, X, and H. If one side was longer, then you would say X and 3X or X and 4X, depending on what the relationship is, right? If the width is 5 times longer than the length, then you will say X and 5X, right? But square base means my length and width of the base are the same, so X and X. So it just depends on whatever the wording is. Okay, let's go ahead and get the volume out of the way because we know that surface area and cost is going to be the one that we're actually working with in terms of the derivative. Okay, everybody good with how we got the volume equation and getting that H by itself, as we know that ultimately that H is going to be replaced in the other equation. Okay, so now we got to build our surface area, right? So remember your surface area is area of each of the surfaces. How many surfaces are we going to have to pay for here? 5 sides, right? You got the base and the 4 sides. It's open top, so there's no material covering the top. We don't have to find a cost for that top. Okay, so here's your surface area equation. The base is x squared. One of the vertical sides is xh. If there's an xh, that means there's an xh behind. And then this side is also xh. If there's an xh here, there's also an xh on the other side as well. So you got your base and your 4 sides. So now that we have our surface area equation, we can start working in our cost for each of the sides. You know that the base is the most expensive one. That's the $15 associated with it. And then each of the other 4 sides are all involving the cheaper material. They're $7 per square meter. So you multiply the 7 in through here, multiply the 15 through the x squared. Okay, so now that we have our cost equation, we know that the h is sticking out. We got to find a replacement for h. So plug in that 30 over x squared in for h. And then now you can start going through your cleanup process, right? You know that you're trying to get your cost equation all nice and clean so that you can get it ready for power rule. Then you find the derivative, set the derivative to 0, solve for x. And once you solve for x, you're near the end of the problem, but we got to go a step further after solving for x. And once I multiply that h replace that h with 30 over x squared. I'm going to clean up that second fractional value. So I get 15x squared plus 840 over x. Okay, so once you have your derivative function, well, once you have your c of x, when you find the derivative using power rule, once you get to your derivative, you set your derivative equal to 0, solve for x. Here I just cross multiplied. Okay, see it. Once you solve for x, you go back and read the problem. The problem says find the cost, the surface area, and the dimensions of the cheapest container. So dimensions means I need x, and h. I already have x, so just find the h equation to plug into. Surface area is the equation right before you built in the cost. So your surface area is x squared plus 4xh. And then your cost, you can just find the cost equation to plug into. Right. So once you solve for x, there's no more creation that's going on, right? You're just looking for whatever the problem is asking. So the most I can ask you are these three things, right? Your dimensions, your surface area, and your cost. And you already have all the equations that you've built from previously to get to this stage. All right, any questions with optimization? Okay, let's do a derivative graph. I'm putting this on page 26, but if you can't find any space, you can go ahead and grab a spreadsheet that I have up here. We're going to do a derivative graph problem from beginning to end where we're going to sketch the f of x, we'll sketch f prime, we'll create our sign lines, and then we'll also sketch our second derivative graph. Yeah.
Will it already give all that information? Like it'll already give everything basic.
Yeah, these are givens. These are just kind of anchor points to at the end when you're ready to sketch your graph. Okay, so we can start off by marking up our graph, right? This is our f prime graph, so we know that this first thing is creating our slope and concavity sign line. You know your x-intercepts is where you're going to target first. So 2, 4, and -4. And don't look at the movement, just look at your location, whether it's above or below the x-axis. So below the x-axis means negative slope. Between -4 and 2, above the x-axis, positive slope. From 2 to 4, again, positive slope. Between 4 and 5, negative slope. F double prime. Okay, so for concavity, we're no longer looking at x-intercepts, we're looking at the what? Yeah, points of inflection. So how do you find points of inflection off the f prime graph? Yeah, okay. Peaks and valleys, right? Your max and mins. So -1, -2, 2, and 3. Okay. To determine concavity, look at the slope. Don't look at the curvature. Look at the slope. Positive slope means concave up, concave down, concave up, concave down. Okay, next up, we're going to sketch our graph, f of x graph, but we got to cover this up, right? This is going to throw you off. If you're looking at this, you're only going to look at your draft is going to come from this. Then you're going to do your draft with the curvature. Okay, so those are my anchor points. I'm going to go ahead and plot those points onto my f of x graph. Yes.
So will we make like the range is gonna be the y-axis?
Yes, but we'll worry about that at the end, right? Yeah, so right now you're just going to just do one thing at a time, just see if you can get the sketch going. And then if we need to adjust with the range, we can, but first one thing at a time, right? Let's not try to do too much. So we know that the graph's going to start off with what? Decreasing until we hit a relative what? Min at -4. So I'm just going to just target a point, my relative min. I don't really care where it is as long as it's my following. And then my graph's going to rise until I hit some value at 2. But it's going to keep rising until it hits what at 4? So maximum. And it's going to decrease until I hit 5. Right. So I know my graph's going to have this shape, right? Decrease, rise, flattens out for a moment, rise, and falls. Now, this is a pretty good sketch of the graph already because we're following the arrows, but the range is telling us my lowest y value should be what? Should be 1. So mine is a little bit too low, so maybe I need to adjust it and just erase it. Make it fit my range. And then my max should be at 10, which 2, 3, 4, 5, 6, 7, 8, which I can just make it a 10 by giving it that tick mark. Okay, so now I can plot my points of inflection. My points of inflection will just land somewhere along my graph. I don't have to create a new path. This path is already laid out. So wherever the graph lands at -2, that's my point of inflection. At 2, point of inflection. At 3, point of inflection. Okay. Retrace my graph. Starts off with concave what? Up. So there's my concave up. Shift to concave down. Shifts back to concave up. And then the rest of the way concave down. Next up, my second derivative graph. And you're only looking at the f prime, double prime sign line. Do not look at anything else when you create your second derivative sign line. And it's going to be relatively simple. You're just going to thread between your points of inflection. To help remind us, above is concave up, below is concave down. On the x-axis is point of inflection. Where am I going to start? Above or below? Above. So you just start above and you're just connecting the dots. That's all you're doing. Do not look at the shape. Just move as simply as you can, connecting the dots, going above and below the x-axis. So start above, go below, back up, and below. We end up below the x-axis. Yeah.
How come it looks like between -2 and 2, it like looks like it's concave, right? It's like going like that.
Remember, this is not the original graph. The original graph is not going to match your shape. Sorry, f double prime is not going to match your shape. The shape is meant for f of x. But if you're dealing with f double prime graph, you guys look at location, right? Because it says concave up. Concave up is above the x-axis, right? Yeah. Yeah. F prime above is positive slope, below is negative slope. Then create your sign line from there. That's right. The location doesn't matter. That's why I asked you to plot your draft first, because then your point inflection will just land nicely on anywhere that you have on your dotted line. Okay, let me know if you have any individual questions. No, I'll give you that prime graph.
And you'll give us all that information.
Yeah, yeah.
So for the optimization problems, we're going like here, why is that?
Well, first I have to write it as this, and then I do power rules. So what's it listed in the hang on the next thing?
It's a negative two.
Yeah, because I got that negative one down.
Oh, yeah.
Power rule.
So, on the test,
Yeah, only if I can really help things like that, like you're not here and I turn over and there you go. I'm always feed that I've been. Okay.
Yeah, no, just say, I think you're.
Are you just gonna study there over there?
Oh, you did. Okay,
Yeah.
good. Thank But on the test, if this problem, I'll give you a homework.
I'm sticking it here, so I can be home for like the first 30 minutes. If you want, it's that spectacular.
At the bottom.
Looking lazy.
That's right. I'll find it.
I'll just tell them my work. Really, I was just a bit of water.
Alpha day tomorrow at 7:45 here, right?
Yes. Try to, if I can get,
Dude.
someone to send out